Slow Friday. Okay, here we are. I think is this loud enough? Yes? Okay. All right, so let's get started. Make this a little bit bigger. Homework 5, due next Wednesday. You have no lab demo due next week. On the other hand, the first bonus opportunity is next Tuesday. And it's certainly doable, but probably not within the section time on Tuesday. So if you want to earn that bonus, you probably should be starting very soon. What else? What's coming up? Oh, midterm 2. All right, midterm 2 is the next Friday. I will post a sample midterm in files, and there will be solutions. Next Wednesday is completely devoted to answering questions, review questions. If there are no questions, it will be very short, a lecture. So think of questions or problems that things you'd like to go over again. Speaking of questions, any questions before we start talking about today's topics? Any questions about Lab 6? Yes?
Any tips besides starting early for Lab 6?
There are a bunch of tips in the web page, the assignment. Be sure to read all of those. Those are very important. Let's see. One tip is if you want to do, so that there's a really easy way to do collision detection between two objects and that you're drawing on the screen, because you'll have a signal for each object, that's high when you want to draw them. So if they are ever high at the same pixel, they will both be 1 at that pixel. And so if you AND those two signals, and if that AND is ever 1, then those two objects overlapped. The only caveat here is that that signal will only be high when the grid counter, when your VGA controller counter is at that pixel. As soon as it moves to the next pixel, if they don't overlap on the next pixel, then it'll go low again. So you have to capture it right away. If that's going to be your signal that the two objects collided or overlapped, then you need to use that, change your state right away. Okay? You might have thought, well, I'm going to take the coordinates and detect when the train is just, when a particular train overlaps with the slug, but that's actually not that simple to do. It's not that hard, but ANDing those two signals is really simple.
Thank you.
Yes?
Do you have any tips on how to start the state machine for early?
How to organize the state machines? Well, so the slug itself should probably be a state machine. All right, and it's going to take input from the buttons, and it's going to need to remember where it is, which track it is, and also, that the track doesn't just jump from the left to the middle. It slides over there. So while it's sliding, that's a state in itself. So you'll need states not only for it where it is, but if it's moving, where it's going from and where it's going to. And of course, you'll probably want an overall state machine at the top level, just to play the game. Something that says, okay, I haven't started. Okay, I'm playing, and oops, I hit something. Something like that. By far the more complicated part of this is the actual trains. Their movement is not complicated, but when they start moving, and there are two trains per track, right? So when the next one starts, so it's not that bad, but that involves the state machine as well. Yeah.
Would you recommend having one state machine just for each track, or should you have like a state machine per track and a train?
So what I would do is just make one track.
Yeah.
And make it work perfectly. The only difference between the three tracks is what coordinate they're on. So make the coordinate an input, and then you can just instantiate your tracks 3 times.
And those tracks should have the logic for each of the trains?
Yeah, they're a self-contained module that does the track, and within each track it has 2 trains.
Would you need any other state machines besides that, like slug, track, and then maybe the overall SINs?
Yeah, I don't think you need one for the energy bar. But if you want, you can. You know, what's a state machine and what's not a state machine is in the eye of the designer, right? It's all flip-flops and gates. Which flip-flops are state machines? You know, a counter is a state machine in itself, right? But you don't think of that as a state machine. You think of that as a counter. Any other questions? Yeah.
What are some like big mistakes you've seen in the past?
Big mistakes. So one mistake I see, well, so when you're starting out, first thing to do is to get the H-sync and the V-sync correct, right? And you've got a test bench that will verify them for you. If you pass those tests for 2 frames, your syncs are good. Okay. If you don't pass those tests, you're either doing something wrong, or it could be there actually is a problem with your counter. Okay, hopefully we tested them enough in Lab 3 that that's not the case, but if we miss something, that could be. The next thing is drawing on the screen. You have to remember that you can only draw in the active region, right? So even though your grid is actually 800 by 525, you can only send colors up to x coordinate 639 and y coordinate 479. If you're sending colors outside this checkered region, you may not get anything, or you may see some stuff floating around. Typically what I've seen is people draw the top border and they forget to stop at 639, right? Because they just check, hey, am I in row 0? Then yeah, turn on the border. But they don't stop at 639. And so the first row looks perfect, but the next row doesn't look perfect. It's kind of slid over. And as you keep going down, they get worse and worse. And then it works fine at row 8 because you're not going, you're doing the vertical borders and they don't go past 639. So those are fine. So typically, I can see, if I see that on screen, I know exactly what's going on. That's a specific pathology. Other mistakes, when you get ready to, let's see, you've done a lot of graphs and grids in your calculus classes. You've actually plotted curves? No? And so you're used to the y coordinate going up, right? But here the y coordinate goes down, and people get confused about this. So if you want to make your counter, if you want to make your object go up the screen, you're actually counting down. So that's a mistake I see. But some of these things are easy to fix. You see that, you know it's going in the wrong direction, you know what happened, and you can easily fix that. Moving things too fast. So that object that's moving up the screen, you need to move it at 1 pixel per frame, or 2 pixels per frame. If you just move it every clock cycle, it's gone. It's nowhere. You may see little sprinkles of it spread around the screen, but you won't really see the shape. That's the most fun one, because you'll see somebody in a lab and they'll display their object, and then they'll push a button which is supposed to make it move, but instead of making it move, it makes it disappear. Okay, other mistakes. Combinational loops. Okay, those are sometimes very hard to find. I think the most common one is I gave you a suggestion on how to detect collision. Okay, so that particular signal for detecting collision will depend on the signals to draw the objects. If you then use that signal to decide that you want to make an object flash, or decide that you want to affect the object in any way, you have a combinational loop. So what you need to do is you use the collision signal to change state, and then the state should have an effect on the object, but not the collision signal directly. Okay, other mistakes. I think that's it. Yeah.
What's the minimum amount of states we could probably use for states?
Minimum, again, what's in a state, right? Depends how you encode, depends how much information you put elsewhere. That's also state. I'd say the worst state machine is going to be your slug state machine. The others are fairly simple. The reason the slug is so complicated is because it's got 3 positions plus an initial non-moving position, a hovering, and then the transition between the positions and which way it's going. Okay, it's a lot easier to have more states than to hide things into signals and try to figure out things from the position. I had this argument with Neil in the lab that maybe several of you heard.
So that would make it like, what, 8 or 9 states?
Something like that, yeah. Yes.
How would we handle the randomness of the trains? Can we use the LFS?
You can use an LFSR. If you're going to use more than one LFSR, you can seed them differently, so they don't all. If you use a bunch of LFSRs and they all start with the same seed, and they all run at the same time, they're all going to give you the same exact random number, which is, not that interesting. So you can seed them. If you don't need to use all the bits, you can use different bits for different things. Lots of different ways to do that. The only thing to avoid is using this exact same LFSR for everything. And
Seeding one LFSR at 0 and then the next one at 0001, would that be a significant change in the random number?
yeah, because the first one would be 0 all the time.
Oh, okay. Well, okay, what about 1 and 2 then?
1 and 2, yeah.
Okay.
Okay. Yeah, so you can just you can actually modify the LFSR to load a seed right at the beginning, or you can scramble the bits. Lots of different ways to do it.
I mean, even just like having them not run until the track
Yeah, well,
loads because the tracks are offset in time.
right. If they don't all run, in lockstep, then you're good too. Any other questions? No. No other questions.
I had one and it slipped my mind.
Oh, okay. Yeah.
Once you get the slug machine done, or like the whole slug object on the screen with all the logic, about how far from finishing the lab do you think that would be?
I think you're about a half to 2/3 done. You certainly can earn bonus 1. Right, that's enough for bonus 1.
Who do you check in with for the bonuses, or do you just submit them?
Oh, you have to show the TAs. The TAs will check you off. If you earn a bonus, you gotta get the TAs to acknowledge that.
And we can do that at any point. We don't have to do it on a particular day.
Well, by the deadline.
Yeah, but anytime before the deadline.
Anytime that they're there working, yeah. Yeah, they won't be there probably on Monday at all. Or again, upload it to Canvas. Any other questions? No? Okay. In that case, I want to talk about cooperating or not cooperating state machines. Let's start with this slide. This is from from Wednesday. Remember Wednesday we did the factorial? All right, I'm going to refresh your memory here. We used our multiplier that we had built the week before to make a component which would calculate the factorial, and it just repeatedly multiplies all the numbers from n down to 1 and stores them in an accumulator, and this huge number ends up in this register. Okay, so this is an example of, of building a component using another sequential component. Okay, and so I want to talk about that in general, and things to look out for and how to avoid issues with this. If I can find my slide. Okay. All right. So we're talking about making a design with multiple state machines. So typically you might have a sequential component that does some task for you, like the multiplier or divider. And you need to use it to do a larger computation, possibly many times, maybe only once. So you're building a system, and you're going to have a control, or here I called it the boss. And the boss is connected to the worker. Well, first of all, these are synchronous. They share the same clock. So we're not talking about anything asynchronous communication. We'll talk about that on Monday. All right, so the boss sends a signal saying, hey, do something. And this is connected to the start input of the worker. And presumably, the worker is supposed to start doing something. And when it's done, it will assert its output ready, which is connected to the WR, worker ready, signal that the boss knows. So now the boss knows that the worker has completed the task, and there might be other connections. There might actually be data connection, where the worker is providing the boss the result, or maybe the output, the data is going to something else, some other component. Okay. so each of these are sequential, and so they're basically state machines in themselves. And there could be trouble. Okay. So one of the things that can happen is the boss you might have designed the boss this way and said, okay, the boss is going to have a state where it's going to wait for the worker to be ready. Because if the worker's busy, it won't pay attention to the start signal. And as soon as the worker's ready, I'm going to tell it to start. So this is just one state of a maybe very complicated state machine. So we're just looking at one particular state we've arrived in called wait. And basically we're monitoring the worker ready, and we'll send out or assert the worker start whenever the worker ready tells us. Okay, but let's look at what the worker is doing. The worker has a chill state, and we didn't design the multiplier and the divider like this, and for good reason. But every quarter, I didn't get one this quarter, every quarter I get somebody who asks, hey, should we have ready be asserted in chill, or just whenever we don't have a start? Could we do that? Well, technically you could. If you do get a start signal, you could say, okay, I'm about to be not ready. Okay, so that doesn't seem like a bad idea, but it really is. And here's why. Okay, if we do this and then we make the logic, well, so the worker start output of the boss looks like this. It's the AND of the worker ready input and the state wait. Right? Worker start should go high if the worker's ready and we're in wait. Over here on the worker side, our ready signal becomes, okay, we're ready while we're in chill and we don't have a start signal. Okay, so what does the logic look like? It looks something like that. Right? We have a flip-flop holding state wait. We have a flip-flop holding state chill. Worker start is the AND of worker ready and wait, which gets connected to start. And then ready is the AND of not start and chill, which comes back and gets connected. And what do we have here? A combinational loop. If boss is in the wait state and the worker is in the chill state, you have a race. And it'll go up and down. And whether anything happens or not depends on whether start happens to be high or not when the clock hits. Okay? All right, so you don't want to do that. And that's why when we design these, we always made ready just depend on chill. And so ready will not go low until after you leave the chill state. And when we do that, the logic looks like that. There's no loop. And there's no race. Okay. But we've created possibly another problem, and that is that we will continue to be ready until the clock hits, whether or not we were told to start. Okay. All right. This leads to the impatient boss syndrome. Okay. So let's say now that your boss is impatient and basically is going to be in a state called do it, where it's repeatedly telling the worker, get to working, start. And it's going to keep telling it to start while it's in this state. And it'll stay in this state until it gets the signal from the worker ready. Now, the way we designed our multiplier and dividers, it didn't matter if we got a start signal when we were busy, we just ignored it. Right? So this this could be fine. Just keep telling it to start until it finally does. Okay, so why is this a problem? Well, the reason this is a problem is because we are going to keep saying ready until we actually start. Okay, so if we look at the simulation of this, so this side, okay. Here's our boss, some state. Our worker is in state chill. And our boss enters state do it, and while the boss is in do it, the worker start signal goes high. And it'll stay high until the boss leaves that state. Okay, so remember our worker here? Our worker is going to, this is the first clock edge where our worker has a start signal. So it's not going to leave the chill state until after this signal. Okay, but that means that the ready signal is going to be high until after this clock signal. Okay, so what's going on here? Well, this means that the boss is going to see this ready signal and think the worker's done. But they're not done. Okay, so this is a problem. You shouldn't be starting it and checking whether it's done or not in the same state. Okay, so what the boss should be doing is changing state. Okay, so when you get the worker ready state, then you go to done. Okay, and only then will you know that the worker is actually busy. Wait, did I make this? Okay. Sorry, this is the slide I wanted. All right, so here we started, and then we went to the wait signal. I don't know what happened. It didn't skip. Okay. All right, so this is what we want to do. We want to change state after we do send the start. Okay. All right, so there's a lot of subtleties here in the communication between the boss and the worker. Anybody taking networks? No? Oh, yeah, so you talked about protocols, right? So this is, did you talk about state machines and protocols? All right, so this is essentially what's important here. And it has to be impervious to delays because of course you have no idea how long the transmission time is going to take. Here it's synchronous, so it's a little bit easier. Okay. All right. Any questions on this? All right, so let's talk about something else. Okay, so you've seen this before, right? You built your own 5-bit counter. It was more complicated than this because it had a load and it could count down as well as up. This one is a very simple count up 4-bit binary counter. It has a reset, which is important. Will be important later. Unfortunately, binary is not the best format to communicate with humans. You don't want your alarm clock to say, hey, it's 8 o'clock, get up, you lazy bones, right? You want it to say 10 o'clock. So a lot of circuitry, an incredible amount, is devoted to converting binary to decimal representations for communication with humans. In fact, there was a group project, a senior project, I think about 5 or 6 years ago, a bunch of students working for Oracle, and they had been asked to create hardware. Because Oracle actually wanted to store their data in decimal form, because it was faster, even though they were wasting bits, it was faster for them to have it in decimal form than to convert it from binary to decimal. Okay. And so this leads to something called binary coded decimal. How many of you have heard this? This is an interview question. So if you hear BCD, you should remember what that stands for, BCD counter. And it looks almost the same as a binary counter. Same inputs, same outputs. I called one ink just so you get distinguished. The only difference is that just like your homework 4 problem, this one counts differently. It just goes up to 9. And then it goes back to 0. And its TC is high at 9 because it's about to roll over at 9, unlike the binary counter, which rolls over at 15. Okay, so we could do the same thing that you did on homework 4 and come up with logic to build this. But let's say we have a binary counter lying around. Let's see, where could that be? Oh, it's over here. So how do can we use this binary counter? I don't want to have to build a whole new counter just for this. Right? When you didn't build a whole new game counter or time counter for your labs 4 and 5, you used your 5-bit counter. Right? I hope. Okay, so this almost does what we want, but not quite. Okay, so let's see if we can just build a BCD counter. Okay, obviously I have to connect the clock to the clock, otherwise I'm going to get in trouble. Pretty much this is probably going to be my outputs. I don't want to have to deal with translating them. Yes?
Reset to B3 and B1.
Okay, so you want... Okay, so B3 and B1. So you want R to be B3 and B1. So are you sure? No, I'm not. You're not sure. Okay.
It's 9, because we don't actually see 10.
I don't actually want to be at 10 ever, right? There's no 10 in that sequence. So I want to go from 9 back to 0. Never at 10, so I'll never be, okay. So reset at B3 and B0, okay. How long will I be at 9 then? Just a clock cycle. Suppose I wanted to count up to 9 and stop. There. Yeah. And CE, okay. Right, so now if I'm at 9 and I'm told to count, then I will reset, which will send me back to 0. Okay? All right, so we could do that. I think that's right. So we still have a CE here. Should I still count? All right. So I want to reset. I think we decided B3, B0, CE. Okay. Wait. That one has a reset though. Oh, what am I going to do with my reset that's coming in? What?
You just OR it in.
Okay, so I want to put an OR gate here so I can still reset this on demand. I forgot to get my whiteout. Don't go anywhere without your whiteout.
Got a white gel pen instead on me.
Okay. All right. Wait, what about CE? So this will force it to 0 if I'm at 9 and CE is high. Put it through a flip-flop, then it's going to be delayed. Well, that's 2 flip-flops. Well, so I have my signal. This is going to cause this to reset. This raises an interesting question. What happens if I tell this counter to both reset and count at the same time?
Does it become 1? Or does it stay 0?
I don't know. You don't know either, right? No one's mentioned what happens. I think we would probably assume that if we were only resetting, it would reset, and if we were only counting, it would count. But
See, I would think about this if I was actually writing the code. But I do believe reset in this case, because it's being ORed with everything else,
yeah,
I think reset's going to take precedence, isn't it?
well, I think
It's equal 0.
this resets.
Oh, but counter enable is not transitioning the state.
Right.
It is simply incrementing the counter.
Right, so if we're at 9 and we get a CE, we're going to tell this to reset. And if I just connect CE to it, we're telling it to count as well.
Does it come down to which of the flip-flops happens to fire first?
No. Don't ever depend on that. If you have a signal like
The
this.
fact that you're pointing it out implies to me that there is an issue with the way it's constructed, and
Well, so the point is we don't have any information,
yeah.
right?
And so it feels like I can imagine a scenario where which one takes precedent is based on which of those 2 flip-flops, because
Yeah, but I don't know how it's built, so I can't assume anything about it.
so that's an unknown.
And besides, all of our logic should have settled, and those flip-flops will load at the same time, and the new outputs will not affect that. So that's not going to happen. It's not a question of which flip-flop gets the clock first or switches first. Okay, so what I've done to be absolutely safe is I've insisted that we can only count if we're not resetting. Okay, so that's kind of safety. Now, if someone were to tell you, hey, reset always has priority, if you're resetting, you don't need to care. You don't care what the count enable is, then I don't need this. I could just connect the count enable. Okay. But without that information, this might be a good thing to do. Of course, if again, now I've made this safe. I've given basically reset priority over the count enable in my new design. What did you guys do anything for your count 5?
Between load and count enable?
Uh-huh.
Yeah, I used a couple muxes, so
And which one has priority?
load.
Okay, that's good, because otherwise you'd have trouble with your VGA counter. right? Because you want to load it, but you want to count all the time. You probably set the count enable high. But anyway, okay, you could fix that. All right, so we did that. All right, so sometimes you can look at a component and figure out what to do. If you can't figure out what to do, there is a procedure to figure out what to do. And it involves something called an activation table. Okay, so this is a new kind of table. We've talked about state transition tables. State transition tables describe the behavior. They're the map of what's going to happen. The state activation table is the instruction manual or the directions how to get from point A to point B. It basically says for a component, if you're in this state and you want to go to that state, you should make the inputs this. Okay, usually what we have is if you're in this state and the inputs are this, this will be your next state. But now we're looking at this differently. If we want to go from this state to this other state, how do we do that? So for our binary counter, this would be its activation table. Right? We have 16 different states, 0 through 15. This is the binary counter. Instead of listing them all, I'm doing it generically. I'm calling them state n, if the value is n. So, and if I want to go to n plus 1, modulo 16, right, because we roll over, I make CE high, and I make reset low. And then I go, that'll take the counter from n to n plus 1. If I want to go to 0, oh, I forgot a row here. Oops. If I want to go to 0, I make reset 1. I should have one more row here. Whoops. Wonder if I could. All right. I'll add it. I have one more row. If I want to go from n to n, what should CE and R be? 0, 0. Okay. Okay, so that tells me how to go from a particular present state to a particular next state. And there can be some overlaps, right? Because if n is 0, then I can either make reset 1 or I can make reset 0. I will go to 0. All right, so how do we use the activation table? Okay, notice that there's some important information in the activation table, which I don't have n again. And that is that R has priority. It overrides CE. If you want to go to 0, you can make R1, and it doesn't matter what CE is. So this actually does tell us that this binary counter gives R priority, and I didn't need that AND gate that over here. I could have just connected CE directly. Let me put this 0 in. All right, so how do we use the activation table? Well, I want to build this BCD counter, right? And this is the state transition table I want. Basically, if the increment is high, if whenever inc is low, I want to stay put if I'm in 0 through 9. But if I happen to wake up with a 10 to 15, I want to go to 0 immediately. I don't want to be in any state higher than 9. Okay? And if inc is 1, then I want to go to n plus 1. Okay, I don't have to worry about modulo 16 here because I'm not ever going to be at 15. And I want to go from 9 to 0. And again, if I'm in one of these, I want to go directly to 0. Okay, and of course I have an output here, which so this is the state transition table. So here what I've done is kind of group a bunch of states together. I've called them N that behave the same. For example, the states 0 through 8 behave the same. 9 is a little different, and 10 through 15 will behave the same. All right, so now what I need to do is look in my activation table to figure out what to make C and R in order to go from this state to this state. Okay, so I add this additional section in my table, which provides the values I want for C and R. And so, for example, I say, okay, if I'm in state 0 through 8 and inc is 0, I want to stay put. So to stay put, I need both CE and R to be 0. So I'm going to make them both 0. To go to n plus 1, I need CE to be 1 and R to be 0. Okay. To go from 9 to 9, I need these both to be 0. To go from 9 to 0, I need R to be 1, right? But C could be either 0 or 1. I don't care. According to this activation table, CE could be either value. To go from 10 to 15 to 0, again, I need C to be anything and R to be 1. And again, I need R to be 1. So now I have the values I need for CE and R in terms of inc and also in terms of the state bits. Right, so I would have to represent each of these with my state bits, the B's or the Q's, and I can write my equation. Well, turns out I can make CE directly equal to inc, which is what we did, right? This was actually inc, and we didn't need this AND gate after all. And I can make R look like this. So why is this different? No idea?
Different from what?
Right, this is the one we did manually by just thinking of what we wanted. Yeah.
Is it so that it resets if you also are in the 10 to 15 range?
Exactly, yes. So we added the feature here that this one would go immediately to 0 if you woke up in 10 to 15. If this one wakes up in 10 to 15, eventually it'll count up back to 0 and you'll be okay, but in the meantime, yeah, it's going to be in the outside of range. So we didn't provide that. If we wanted to provide that, we would have another OR here, which is basically Q3 ANDed with Q2 or Q1. Right. Okay. So I don't know if you want to attempt to do this one. No? This is a little bit harder, right? Because now I want to build a BCD counter that can go up and down.
It's not that much harder. You just add a couple more. I mean, it's longer for sure,
It's more involved.
but it's not more difficult because, you're not dealing with the arithmetic difference. It's just more states.
more conditions. I didn't add any states, right? We're just controlling
Yeah.
the sequential machine with
But more
values. Okay. So in order to do this, I needed my binary counter to have a few more features. First of all, I wanted my binary counter also to be able to count down, because otherwise there's no way for me to go from 8 down to 7. I could only count up or go to 0. All right, and that's not enough. So sometimes you can't use the component. It doesn't have enough functionality for you to use it the way you want. If it has a load, you're always golden, because you could always load whatever state you want. Of course, then you might as well be used. If you find yourself doing a lot of loads, you might as well just have used flip-flops. Right? No point in having to deal with managing this counter if you know what you want and you're going to load it most of the time. Just use flip-flops. So hopefully we'll be able to use some of the functionality here. What do you think? You want to do this? No? I got 15 minutes. Yes. I have another binary counter here. Of course, I have to add a bunch of things. First of all, a load, up, down, and a DN. Okay, so the first thing is I need to describe my transition table. Okay. So here's my present state. And then I have combinations of increment or decrement. Right, so I'm building a BC counter with an increment, decrement. Well, let's ignore the reset for the moment. Okay, so if these are both 0, right, then, and this is my present state, then I'm going to stay there. If these are 0, 1, meaning I'm decrementing, then I want to go to n minus 1, right? Yeah.
So is the increment, decrement 2 bits then?
Yeah, they're two separate. Okay. I am building. Where'd my mouse? We're building this component here, right? And it has inputs increment, decrement, and reset, which I'm ignoring because I don't want to have 8 columns. Okay, so increment. So this is also increment, decrement. All of these are pairs. Okay, so I want to subtract if decrement is 1 and increment is 0. There are 2 other possibilities. However, I am going to arbitrarily decide that increment has precedence, which means it doesn't matter what decrement is. If increment is high, I am incrementing. Very positive person here. Okay. So that's what I want to have happen. And in the binary counter, this will work perfectly if we are in states 1 through 8. Actually, will it work for 0 through? No, not 0. Okay. So, all right. Now, I need to decide what I need CE, up, down, load, and D in to be to make these things happen. Okay, so if I'm in states 1 through 8, and I want to go, okay, I need 3 sections here. right? So this is 0, 0, 0, 1, 1, 0. All right, so if I want to stay put, I don't want to count, and I don't care what up and down is, and I don't want to load, and I don't care what DN is. Actually, should have been a don't care there. Okay. If I'm going to decrement, then I need CE to be 1. I need up, down to be 0. I need load to be 0. Right? And if I want to increment, I need CE to be 1, up, down to be 1, load to be 0, and increment. Sorry, and DN to be 0. Okay. All right, so let's see. We have also 0.